Just benefits.
All right.
Oh, okay, that's right. Yeah.
So here's what we're going to do. Remember that I told you it's going to be like speed dating? This part you are going to hear fast from several faculty, and we are going to start with Dimitris.
Hi guys. Okay, to be honest, given the speed you are going to hear information, if you remember just one thing, if one of us says, that would be a miracle. So I would like you to, because I personally will meet with all of you, so please remember something that caught your attention and bring it to the meeting. I kind of doubt that I have time to tell you. So that's what I believe. I believe in positivity, optimism, and can-do attitude. I don't like negativity. That's an important component of the story. In terms of topics, so I have several. I work on precision medicine from observational data. The golden standard in medicine has been clinical trials, randomized clinical trials. In the last 100 years, the complication is that these are extremely expensive, which is the reason healthcare in the US is 20% of the country's budgets. So, but observational data are ample and very available. So we have published some work recently. I call it The Road to Personalized Medicine, that appeared in a recent version of Nature, that I think makes a progress of how to use observational data to make personalized treatment, not just if the drug works, but for which parts. So if this catches your attention, it's an interesting one. The second one, who here knows the company Theranos? Have everybody heard of it? So Theranos was a company that proposed or claimed that from a piece of blood, you can actually detect all human diseases. In its heyday, had a market capitalization of about 10, 12 billion. It was a complete fraud. The person is in jail. So we actually, the objective of this research is to do Theranos without the fraud, to do it in solid scientific grounds based on AI and based on genomics. So, so we have made good progress on, you have some blood, and we can detect from the DNA using AI methods, multimodal actually AI, cancer, diabetes, early on. So we are trying to validate it with real world data, but I think it's a pretty exciting story. And not only on those, on all of medicine. That's number two. Third, multimodal AI. What is multimodal? So traditional work has been on tabular data. You know, I bet many of you have taken statistics courses where the inputs are numbers. However, what is available in the real world, take climate, for example, predicting hurricanes. We have, of course, historical data in time series. We have pictures from the Earth of hurricanes. We have language. These are reports in Wikipedia, in books, and so forth. So there are multiple modes: language, images, tabular, in time series, genomics, and so forth. We have, in earlier work, we have published another Nature paper on combining this data for better predictions. Medicine is like that. Medicine is multimodal. So how do you make this prescriptive? How do you make decisions based on that? Which treatment you should give to a patient? Based that, this is trying to emulate the human experience. If you go to a doctor, you would like the doctor to utilize everything in their disposal. So if this captures your attention. These days, I am responsible for what is called open learning. I'm the vice provost for open learning at MIT. This is what MIT does in education outside of a residential environment. So we have launched AI as our first effort, which is going to launch in September. But part of this effort, we are doing personalization of education. Personalization of education is not feasible in a classroom of 200 people. What my friend here wants to hear and what you would like to hear might be different, or the way you understand things. So how do you personalize education via Gen AI? Very exciting new area, which I think has been enabled by the fantastic developments in AI. And these are some other topics that, this might actually, because this is different, for those of you that are more mathematically inclined. And this is something I think it's worrisome. Take LLMs. There are 5 companies in the world, if you consider DeepSeek, maybe 6, but 5 companies that are capable of training these large language models. Universities are not in this game. We cannot afford it. The cost is in the tens of millions. So, you know, if this continues in this way, and it becomes larger and larger and larger models, like these days I heard that OpenAI is now training 70 trillion parameters. Trillion, I mean, we are in the deep end there. So, so the question is, my belief of why this is the case is that we don't, the methods we have to solve these very large parameters, there are different optimization phenomena happening when there are many, many parameters. The key here is that local minima disappear. So trivial methods like steepest descent work. But this necessitates very, very large models. And then we need to use GPUs, expensive things. So I believe the following is feasible. And I have evidence on that. You can train models with few millions of parameters that compare in performance with large, but trivial optimization methods do not work because they are deep local minima. So you need to utilize our knowledge of optimization to do that. That's an interesting topic, in my opinion, for those that have interest of doing something in warehouses of theory inside. And I'm now the end.
Thank you.
Of my time. Thank you.
The next person we will hear from, thank you, is Kathy Wu, please.
Thank you. Hi, everyone. Hi. Whoa, good group. My name is Kathy Wu. I'm an associate professor here. I am as new as you to the ORC, but not to MIT. I've been here for a few years. So I'm affiliated with LIDS, CEE, and IDSS, and as of this year, affiliated with the ORC, and you'll maybe see why. So I broadly work on the intersection of AI and transportation, and a lot of transportation involves modeling really complex, large systems that involve interacting, intricate human behavior. So that's what I largely work on. So a lot of these systems these days that we want to model are so large, so complex, that it is very difficult to manually model these systems. So what I want to convey to you in a few short minutes is why the classical paradigm is being stretched to its limits and what AI can potentially do to help. And then I'll break it down into the areas that I work in. If you're interested, happy to chat more. So I call this AI for system modeling. So first let's talk about system modeling without the AI part. And just to motivate this, you can have a couple examples in your mind regarding, say, delivery, logistics type systems, or traffic management systems. And we're interested in innovating upon today's systems for next generation systems. So the classic paradigm of system modeling involves taking a problem that you're interested in, say, your next generation one of these, and it involves simplifying the problem into some existing model-based framework, a lot of the coursework that you have taken, that you will take in this program, and then solving it using these model-based tools, analyzing the result. But because of the limitations of model-based frameworks, we had to do quite a bit of simplification of the problem. And when our problems become more and more complex, the simplifications become more and more different from the problem that we originally cared about. So then we have to take care of this loop of reintroducing complexity so that it's close enough to the problem that we originally cared about, so that it really informs the engineering design decisions. If I were to put time on these components, I would say once you've taken the coursework, modeling the problem takes on the order of weeks. It's not so bad. It could be faster, but it's okay. Solving it, these solvers are great. These are great courses that you're going to take. So solving it is very fast. The really slow part is reintroducing that complexity that these frameworks struggle to handle in the first place. So this is where a new paradigm potentially comes in, And we can think of this as AI-assisted system modeling. The components are largely the same, but now instead of modeling into a model-based framework, consider casting it into a model-free framework. These are frameworks that are a little bit looser, not so confined to a particular mathematical structure. Then, when we want to solve these problems, we can no longer use the really awesome model-based solvers. We have to use something more model-free, like reinforcement learning. So if I were to put times on these, now modeling might take a little less time because fewer courses are required. Solving now takes more time, but the real benefit potentially comes in the reintroducing complexity. Now if I at first studied a one-lane road and I want to add a second lane, I might not need to go back to the drawing board and reintroduce new tools into my model-based framework. So now this goes down from years to days. This is not something that we have today. This is something that we strive to achieve in my research group and in related research groups. Also, I should just mention that in the age of large language models, we can potentially drop this days down into minutes by literally just telling ChatGPT, like, add another lane, make it an HOV lane, and so on. But my core focus is on getting this down from years to days. So this is a big research area. So let me just convey broadly the ways that we're tackling this. If we look, the essence of what we need to do here is to make it easier to solve a new optimization problem. What underlies transportation systems problems is just hard and a lot of different optimization problems. So given a new variant of a vehicle routing problem, given a new variant of a traffic control problem, how long does it take for me to derive a new solver, a new solution? So if I look at the optimization solver landscape, we can map it onto the axis of how much work does it take to define a new solver. So a lot of work or less, not very much work. And how effective is this solver? We want it to be easy and effective, right? So in the interest of time, I'll be pretty quick. There are three classes of solvers, broadly speaking. Pure learning. These are actually not very effective right now. The model-based solvers that you're going to take lots of courses on, pretty good. In industry, and when you talk to practitioners, there are also specialized heuristic solvers that are highly specific to a particular problem that often are very, very effective, but also expensive to create. So what we do in my group is we're addressing some of the fundamental limitations of these pure learning approaches, in particular addressing training reliability of deep reinforcement learning. We're also taking these methods that already work pretty well, and we're hybridizing them with machine learning to make them even more effective, and then we are applying these to increasingly challenging mobility problems, and it's sort of a virtuous cycle that reinforces one another. So if any of this is interesting, happy to chat. Thank you.
Great, thank you, Kathy. Next. Hi,
No
Hao.
time to clap.
Yeah, no time to clap. Hi, Hao Liu or Sean Liu.
Yeah. Oh, hi.
We
So
call him Sean, but he goes by Hao Hao. Hi, Hao.
hi, how?
Yes.
Yeah. Okay. Good. Good. So first, welcome. It's a great, big congratulations. I think I was a student here about 10 years ago. It's definitely a wonderful achievement for being here even. Okay. So I'll talk a little bit about my research. But first, let me ask you guys, how many of you know what is linear programming? Oh, all of you. Good. What algorithms or what solvers do you use? Do you know?
Yeah, depends on the problem.
Depends on the problem. Okay. Good. Good. Okay. So we probably know that on the one hand, machine learning grows crazily in the past 10 years, right? We know about ChatGPT, all of these deep learning ideas. And on the other hand, for linear programming, probably use Groovy, simplex method, barrier method. The size of the problem one can solve is about 10 million variable, but for deep learning, it's about 1 trillion. The size is very different. But on the other hand, if you are familiar with linear programming, you know that linear programming is a convex, nice structured problem. Deep learning is so non-convex, very high dimension. So there is clearly a mismatch, right? So one should be able to solve a much larger linear programming than deep learning at least. Okay, So what is the fundamental reason? Okay, the fundamental one of the most maybe one of the reasons may be the hardware. Okay, so for deep learning, we use GPU, TPU for training, and you have like a few thousand core. One GPU have 5,000 core, and like we're gonna use 1,000 GPU. On the other hand, for like mathematical programming, linear programming, for example, people still use like a single machine. Like Groovy can only be run on a single CPU. It cannot run on like two CPU even. Okay, so this is like one of the fundamental reasons, like what is going on, like why we are not able to solve like larger like linear programming or other mathematical programming problem. And the reason for that is because the traditional method, like simplex method or interior point method, they are not designed for utilizing parallel computing. They are designed based on like sequential operations. And like my goal is more like trying to develop like the next generation optimization algorithms by taking advantage of GPU and distributed computing. So there it's required to design new algorithms that can be easily parallel. And furthermore, our goal is trying to scale up like maybe 1,000 times the size of a problem I can solve by using parallel computing, and also think about 100 times faster than the like state-of-art solvers. Okay, so to achieve it, we need to design new algorithms. The new algorithms need to avoid some of the sequential operations that is the bottleneck for simplex and interior point method. I think like because you know what is linear programming, you know like the impact of it already. So, okay, so I just want to talk a little bit more about the types of research I personally like. Okay, it's almost there. Okay. Okay, so I like two types of research. One is the fundamental theory, and particularly elegant theory that can be easily taught in graduate level class. Another thing I like is like practical solvers development that can have a practical impact used in many companies in the world. Like if you are interested in it, take a look at these blogs. These are some like introduction for some of like my work utilized by other companies. Okay, and like what I'm looking for students is more like hardcore optimizers. We are not like users of Groovy, but rather we are building up Groovy. Okay, I think I'll end here.
Yes, thank you.
Yeah.
Thank you, Sean.
Thank you.
Okay. I told you it's like speed dating, and I think it sounded like I was kidding. So, next it's me, and of course you are hearing from me today, tomorrow, you'll get enough from me. But what are my interests? My interests are to work on important applications. In particular, the three application areas that I work on involve health and healthcare, involve retail and supply chain, and involve also sustainability and climate. So in terms of health and healthcare, I work with two hospitals, namely UMass Memorial Hospital and Tampa General Hospital, looking at problems such as, for example, critical diseases, like for example, take sepsis. Can we monitor the path of a patient to try to basically understand at each point of time what are the right treatments to give them? And this is not just particular to sepsis. And you're trying to do this to make sure that people do not die. Now, there are underlying theoretical frameworks on all of these problems that you can actually develop, as I have grown to find out. In my early life, I worked on theory, in my early career, I should say. And then I realized that actually you can develop the best theory if you link it to a very practical application, and then if you're actually able to implement and get somebody to use it. So you get two birds with one stone. So, for example, the context of sepsis involves reinforcement learning, and how do you do this type, solve this type of approaches and make it practical and solvable fast? And how do you do it on something that also Dimitris Bertsimas mentioned before? What you have available is observational data, and getting, randomized control trials because you could be risking somebody's life is actually kind of an issue. That's just to give you an idea. Also, let's take supply chain. A company I work with is actually Zara. How do you actually manage the supply chain operations? How do you do this in order to, they send articles twice a week to the stores. And then the managers, they give them freedom to decide what they want to do, although they give them recommendations? Can you actually understand how these managers behave and take this into account when you decide what items to get? These type of problems. Promotion planning is another area. You know, how do you design your promotions in the clearing sale? Because you don't want to promote the items too much, because then your customers are going to be turned off. And in terms of theory, all of these problems means that it's machine learning and AI as it intersects with optimization. And there are many theoretical problems because you want to come up with something that's theoretically sound, but yet is interpretable, it's accurate, solves fast, looks like you are looking to have everything done at the same time. My style of advising is, I'm flexible, it depends on the student. I do like to have a fixed weekly meeting with my student, regardless of additional meetings on the different problems they work on. Impact with theory is important to me. I mean, I have been working for now the past 27 years and have graduated several students from the ORC who have either gone to academia or industry. You are going to meet with me, most of you, and you can ask me many questions. But I think on this note, I want to introduce Alex.
Thank you.
Alex Jackie, yeah?
Yes. Hi. Thank you, Georgia. With me? Yes. Hi, everyone. Looking forward to meeting you all today, tomorrow, tonight. I'm Alex Jackie. I'm an associate professor in operations research at the Sloan School of Management. Also, a stupid man who thought that biking today would be a good idea. But I lead a research group on large-scale optimization with a focus on different application areas: transportation, logistics, decarbonization, social good. So I'll talk a little bit more about these different areas. Roughly speaking, what my group does, everything that we do in the group has kind of a dual intent. One is solving important problems, because we work with companies that are facing important problems, because we are aware of important societal questions, and we are trying to develop tools that can address these questions. So we take a fundamentally problem-driven approach and we try to solve some of these problems. So that's intent number one. And intent number two is, in order to address these questions, we need to develop new methods. More often than not, if these problems are problems, that means that we don't know how to solve them, right? So, and when we start digging a little bit, then we need to we need to look into how to model these problems, how to solve them, and then at some point we hit like a big bottleneck. The problem is too complex, we don't know how to solve it with existing methods, and therefore we need to develop new methods. Roughly speaking, these new methods in my group primarily fall into the realm of large-scale decomposition methods for optimization, vendor decomposition, column generation, and these type of things. So integer, stochastic optimization methods with a focus on algorithms. So how to design these algorithms, how to make them converge, how to derive guarantees of exactness, how to get an upper bound and lower bound so we know if we have a good solution or not, as opposed to heuristic methods. And then how to implement them efficiently, how to make them work with data, and that's where we connect back methods with practice. Few sample applications: microtransit, so how to design and operate hybrid systems between transit and ride sharing. What does that look like and how to design it? How to make transit flexible, basically. So we have a couple of partnerships there. Decarbonization, so in particular these days I'm very interested in cloud supply chain. So I have one student who will be interning at Microsoft Research this summer, so we're continuing our collaboration with them. Cloud supply chains just overtook aviation in terms of greenhouse gas emissions, so there's quite a bit of power utilization questions that are central here. And other social good applications, so right now we have two ongoing projects. One is in the realm of organ transplantation, so how to really take organs from point A and bring them to point B in time, and how to organize these logistics with like very complex coordination requirements between surgeons, machines, patients, and others. And wildfire suppression. So we have one paper that is finishing here, and then there is more to be written here. How to allocate crews in order to suppress wildfires with maximum efficiency. So if you're interested in these methodologies, these applications, I look forward to meeting with you today. I think that's my time.
Thank you.
Well done. In terms of time, Alex. Thank you.
Thanks everyone.
And next is Daniel Freund, and there is a clicker here. So
I don't need any clicking.
you don't need any clicking? Good.
Welcome, all of you. Congratulations on being admitted to the ORC. My name is Daniel Freund. I work on two broad areas at this point. One is the broad area of mobility. The other is the broad area of nonprofits, and in particular, what I'm most interested in, at least currently for now, in this space is immigration. So let me talk for 2 minutes each about each of these two, and if you're interested in talking beyond that, I'm happy to chat during our one-on-one. So if we don't have a one-on-one scheduled, feel free to reach out. My email address is on the slide. So in mobility, I've done a lot of work in the past on bike sharing and ride-hailing. If you've used a bike sharing system in the US, you've probably benefited in one way or another from some of the algorithms we developed. In ride-hailing, I've done a lot of work, in particular with Lyft, working on various of their sort of real-time algorithm challenges, such as pricing, matching, and so forth. Nowadays, in the mobility space, what I'm most interested in is the deployment of autonomous vehicles. So I've been in this space for getting close to 10 years, and at some point you want to start asking new questions. You don't want to write another paper on how to price a ride in a ride-hailing system, but there are really interesting questions about autonomous vehicles that are fundamentally different from sort of the traditional questions. To give you some examples, if you are Waymo and you're deciding to deploy your autonomous vehicles in a city, what part of the city do you want to cover? If you are deploying human drivers, it's sort of easy because they can drive everywhere. But autonomous vehicles need to be trained on the road segments that they are driving on. That's called mapping. And you need to decide, well, where do I want to do the mapping? Because doing it everywhere is too expensive, but you need to do it sufficiently so to cover a large amount of the demand. So that is one question I'm very interested in these days. Other questions are, how should Waymo and Uber be structuring their collaboration? That's very much a market design question. So you can tell there's some optimization happening here, some incentive and market design happening here, and some modeling happening here. And that is sort of all present in the mobility work. Let me switch to the immigration work. So an aspect of immigration that I've gotten especially interested in over the last few years is the scheduling of asylum interviews. This is going to sound very bizarre. What is there to do about the scheduling of asylum interviews? It turns out that scheduling decisions of asylum cases have tremendous impact on millions of people that are affected by them. So in the US, you have a backlog of about 1 million people that have applied for asylum and are waiting for an interview. In fact, that is for a particular kind of asylum. There are different kinds of asylum. I'm looking at affirmative asylum. And this backlog means that people are sort of in limbo. They can't really move on with their lives. They want to, maybe start college, but they can only do so once they've been granted asylum because they're not eligible for certain aid. It's important that people get this service. And it turns out that for most of the last 30 years, these cases have been scheduled in LIFO order, meaning the last case that occurs is the next case that's going to be scheduled. That is very bizarre, right? So there must be a reason for that. And what I try to do in this line of research is try to understand that reason, try to model that reason, and try to then say, okay, if we believe that people are right in how they're thinking about the system, what type of scheduling policy is actually a good idea, what would be a bad idea, and then coming up with new insights for how to schedule, for how to organize the asylum scheduling. With, I think, already we have some very interesting results that are sort of at the interface between public operations and rational queuing and, I guess, optimization. So I have these very different threads of work. I'm very interested in finding a student who's interested in one of the two, and happy to chat more about either one.
And very well with time.
With the time? Good.
Yeah. Thank you.
Thank you.
And next we have Erzo.
Okay.
And this is it.
Hi everybody, I'm Retzef. I'm here quite some time, and okay. So I wanted to start with very quickly describe to you what I'm getting excited about, what get me excited about research, and in general this is really about complex systems, and I really try to be motivated by practical problems. I'm very interested in broadly speaking, in things that are related to human health, like healthcare systems, pharmaceutical, food, agriculture, and water. I have a lot of activities there. I'm very interested in risk management, and I'm really interested in how machine learning, artificial intelligence, and optimization can be used to inform both policy as well as business practices. And I'm very interested also in combination of theory that is being inspired by practice. And I also give in the slides that I'm not going to go over now, but in the slides on the Dropbox and will be printed, you will see examples of projects that I've been working on. But I thought that one way to kind of illustrate what I'm like, what kind of research I like to do, is to tell you about the specific example that this is really a paper that is about to get accepted with the student that is graduating from the ORC this year. And it's really motivated by zoonotic viruses. If you all heard about the bird flu, this is kind of the next concern of the next pandemic. This is an example of a virus that emerges from animals, and if it mutates and is able to infect humans and then mutates again and is able to infect humans to humans infections, that could cause a big problem. Bird flu is one example, but SARS in the past, swine flu, there are many examples of zoonotic viruses that cause major problems. And one interesting fact is that many of these outbreaks emerge from China, and specifically from food markets. And speaking of which, a lot of my project is actually internationally positioned. So I work in China, I've been working in China, in India, currently I work in Thailand. So my students also get to see the work more often than not. But one thing that was intriguing for us, that if you actually look on current epidemiological models, they don't explain why markets are serving as an amplification point in the supply chain for zoonotic viruses. And even when you have farms that supply the market with very low infectivity rate, it turns out that somehow in the market this infectivity is going up. So what we wanted to do is to develop a model that may explain the mechanisms of that. And I'm going to give you some very pictorial picture of that. So the picture here, you have many, many small farms with very low infectivity rate. This is kind of the brown bird. And they get into the market on a given day. And within the market, there are multiple infections mechanisms. One of them is infections between infected individuals and healthy individuals. That's kind of the classical mechanism that we all kind of learned about when we talked about COVID, right? Like we can infect each other, right? But the interesting thing here is that in addition to that, there is also infectivity from the environment, because the virus can actually stay in different environmental components like the water, the cages, and that environment can infect the individuals, right? And then these individuals that were infected shed infectivity to the environment. And then they leave the market, but as you can see, the rate of infected individuals of the outflow is much higher than the inflow. And then this actually continues, and what is happening here, that the environment is becoming more and more infectious, and therefore you get this amplification. This kind of interaction between the environment and the infected individuals is a key mechanism here. And we actually established the theory here. We built the model that can be parameterized. We actually proved some structural properties that actually this system can be in three states. One where the infection is very stable. The other one when it grows very, very moderately. And the third one is that it's actually exponentially growing. And that's kind of when you're likely to have infections. But you also showed that the frequency of sanitation that you have in the market is actually very, very critical here. Okay? So just, again, giving you an example. Policy impact, very practical problem, theory, modeling, and very practically kind of you go to there and you have practical recommendations for policies. You will see more examples, and I'm happy to talk about more examples when I meet with you. Thank you very much. Welcome to MIT.
Wow. Very efficient. And 1 minute early.
I'm happy to,
Yes,
whatever you cannot say in 4 minutes, you cannot
Yes.
say. And see many of you later. So.
Yes.
See you.
And next is Rahul Mazumdar and
Hello everyone.
wait.
First of all, congratulations to all of you for being accepted to the program. How do I use this?
You just
I have just key.
yeah, that's okay. We all have to. Yes.
All right. So I'm Rahul Mazumdar. So I'm in the OR and STAT group. So I work on statistics, machine learning, as well as optimization. And I know statistics, machine learning, and optimization is very broad. So to give you an idea of the areas that I work on, some of the publication outlets that me and my group and collaborators started. These are core statistics outlets, like the Analysis of Statistics, Analysis of Applied Statistics, ML conferences. So these are some of the ML conferences that some of our work appears in. And then we also do research in pure optimization. And these are some of the outlets that our works appear in. We also work on methodology that can be applied to various, in various domains. To that extent, these are the scientific areas where we publish in. These are collaborations that we have with people at the Harvard Medical School and Harvard Biostatistics as to how will you use ML and statistical methods in the context of genetic problems and so on and so forth, right? To understand diseases and so on and so forth. All right, so research interests, I have a long-standing interest in methodological aspects as well as theoretical aspects of both statistics as well as optimization. And over the years, the specific problems that we work on, they have been changing. And these have been mainly inspired by collaborations that we do, both with industry people as well as the applied sciences. Right? So to give you an example as to what are a very simple example of a core methodological problem or a core optimization and statistics problem that my group has been working on. So think about a linear regression problem. Right? We all do linear regression. There is a response and then there are lots of independent variables. Now let's suppose I give you a very simple task. I say that out of all the independent variables, not all independent variables are useful. A small subset of the independent variables, let's say 1% of the independent variables are useful in explaining the response. Okay? So now it's a selection problem. What are the independent variables do I select out of potentially thousands or millions of independent variables? So that is a discrete problem. How do you select? Okay, it's an optimization problem. That, it turns out, is one of the very core problems in statistics. It also appears in other places. For example, I give you data on stock returns over time. I want to understand how these stocks are related to each other. It can be dependence, it can be independence, it can be conditional independencies, so on and so forth. So these can also be modeled with discrete optimization problems. Okay, so these are very core and foundational problems. Recently, via collaborations with Google AI, now this is a group of people in Google Research, Google DeepMind, and recently we are starting a collaboration with Google YouTube. So the problem is, you have these very large language models or recommender system models. These models are very difficult to deploy, okay, because they have too many parameters. So the question is, do you really need so many parameters to get a performant model? Or can you get a good performance with a model which has a fewer number of parameters? Okay, so let's say concretely a 70 billion parameter model that has been released by Meta. Okay, do you really need 70 billion parameter model to do a good job in your specific application that you care about? Or can you do it with 100 million parameters? Okay, so you see number of parameters that you start with is very large and you reduce the number of parameters. And of course you want to reduce the number of parameters so that the model efficiency is not lost. Okay, so the first problem that I talked about, regression with feature selection, has very close parallels with this particular problem that I'm talking about. And these are some of our methods that we have developed in our group as well as in collaboration with people at Google. Some of these have actually been deployed now. So if you go to LinkedIn, for example, Some of the compression methods are actually currently running over there. So optimization, how is OR? So broadly speaking, I think optimization OR methods, like algorithms, the way in which we design them, they can actually have a big role to play in these AI applications. Even though apparently we're at a high level, they don't seem to involve optimization, but these core methodologically grounded methods can have an impact, can have an important role to play. So this is basically the mix of problems that we work on, and you can see that there are lots and lots of topics over here, but foundationally, some of the tools that are used, they kind of are common across different problems. Okay, so basically OR, optimization, and statistics in these out there in the wild can also be useful. All right, thank you everyone. Once again, congratulations, and I look forward to meeting many of you today and tomorrow.
Thank you. And next we have Harap Olimata, a name I can pronounce Welsh because she's my fellow Greek.
Okay, thanks Georgia. Congratulations everyone for being admitted to our program. I'm very happy to be here and to be talking to you today. So my name is Harap Olimata. I'm an assistant professor at the Operations Research and Statistics Group here at MIT. So let's talk a bit more about what my research is all about. So I focus on algorithmic decision-making systems when humans are involved. So what happens a lot of the times in the settings that I study is that humans provide their data to these algorithms, and these algorithms are tasked with making decisions that are important for humans. These decisions can vary from like loan approvals, hiring decisions, benefit allocation, recommendations in recommendation systems, and so on and so forth. Now, when humans understand that they interact with machines, with an AI algorithm, they sometimes try to best respond to this algorithm. And my research is studying a lot of different behaviors of humans against these algorithms. I study humans that sometimes are strategic, myopically strategic. Sometimes they behave in ways that we believe are irrational. If we think about, the standard microeconomics view of the world that we have in mind. Sometimes users try to be non-myopically strategic. We see that especially in recommendation systems where users try to choose the content that they see in order to steer the algorithm one way or the other. But also I study a lot how users' preferences evolve in these systems. Now, this is not just for making better decisions for these users, but there are effects of these decisions that feed back to society. So there's this feedback loop that is created, and my research studies the following three components of this big feedback loop. On the one hand, I try to make decisions that are better for humans, that are active participants in the AI systems that govern their lives. On the second aspect, I try to study methodologically and provide theory for what are the byproducts of this human-AI interaction that can sometimes go wrong to society at large. And lastly, something that I'm really interested in, especially with regards to the generative AI boom and revolution, is how can we as theoreticians provide concrete policy recommendations and be in the room with regulators so that we can advocate about a better human-AI collaboration. And I've alluded to that, but my research has this weird mix of methods and tools that I use. So I started as a theoretician. I built models of the world and I proved theorems about them. And then gradually I started grounding my models of the world to social science experiments. So I do a lot of work with interviewing people, almost like an ethnographic studies of how people interact with these human AI systems. And finally, very recently, I've started being involved with more AI and government regulation about how can we regulate these generative AI systems when they interact with humans. And the interesting thing that I find in my research is that I try to keep this interplay very close and very linked to each other. I try not to think of each of these. You won't see me writing papers that are just only on theoretical models. And some domains, application domains that I have already alluded to, but I have significant expertise in recommendation systems and AI policy, especially with regards to auditing for social media platforms, auditing for generative AI products, and so on and so forth. And this is my dog Tara, who is a very important part of my lab. And if you would like to see more about what I do for research, you can go on my website, and you can also read my advice in philosophy in this short document that I have posted online.
What if I want pictures of the dog?
And
Say
yeah,
that.
I was going to say,
What if I
can
want
we
pictures
also
of the
speak
dog?
to the dog?
Yeah, 100%. I was actually thinking of bringing her in today, but I decided that it's going to be very chaotic. But she's a, for those of you who are going to meet with me later today, you're going to see her bed and her toys in my office. She's a regular. She's a regular.
But she's going to be a later surprise.
Yeah.
Yes. Okay, thank
For
you,
those of you
Mara.
that accept the offer. Oh,
Thank you. Thank you.
I mean, I said it, right?
There you go, of course. I didn't object. And next we have Andy Sun. All you have to do is use the clicker.
Oh.
Yeah.
Okay, great. Hello everyone, welcome to MIT and OR Center. My name is Andy Sun. So I think you choose a great discipline, or operations research. It's really a key discipline in sort of solving real problems with rigorous, systematic, and creative methods. So one of the biggest real problem, I think, is climate change. And here in the middle part here, it's probably too small for you to see, or you probably have seen this. This is a projection of carbon dioxide emission over the next couple of decades. And the trajectory that we're on is quite concerning, that it's keep rising like this way. Where what we really want is not only slower rising, but actually decreasing. So you see the difference. And what we really want is to hit mid-century with zero net emission. And that's a huge change, because energy system really underlies everything that we're doing in modern society. So my research basically looks at energy system, in particular the electric power system, and its related infrastructure like transportation and buildings, and look at how to decarbonize. And you think this may be a pretty easy problem, but actually not, because the system is so complex. It involves many moving parts. There are a lot of participants, there are market structures there, there's an infrastructure, physical system there. So it's really an economic, engineering, and a social system. And from our OR perspective, we can really model many parts of this through our discipline. For example, we can model markets with distributed agents, we can model discrete decisions, we can model uncertainty, as we see there are a lot of uncertainties both in short-term operation of the system and also long-term how people are going to change their behavior. And a lot of mathematical structures here really is the underlying challenge. So I work a lot with the energy system operators and utility companies and tech companies more and more these days. As you know, all the AIs that drive up the energy needs. So there are many different kind of problems. You don't need to read this in terms of the horizon of decisions from seconds all the way to decades. All these problems can be modeled in operation research or optimization, and use a lot of stochastics, also statistics. So I also do a lot of research in fundamental optimization. So here is kind of a categorization of what we think about, how we think about optimization from both static problems with deterministic parameters and convex structures, which is sort of the nicest problem, to still deterministic, but discrete or continuously non-convex and discrete non-convex, and all the way to, you have dynamics decisions that you need to make, there are uncertainties involved, there's non-convexity involved. So I think the field is moving toward this corner here where we're looking at all these combined complex factors together. And our group has been developing algorithms in all these different categories. I think that could be a fundamental contribution in terms of addressing the underlying computational needs to solve all these problems. Okay, all right. I look forward to meeting with you all in this couple of days. Thank you.
And next we have Swati Gupta.
Thank you, Georgia. Hi everyone, welcome to MIT ORC. I am a little bit about my research. So I work on two broad areas of reliable, robust, and trustworthy AI and algorithms. And I also work on fundamentals of efficient optimization and learning. So what are the kind of questions we look at? So we think about various domains and various applications there are often problems with biases in data, uncertainties in data. There are problems with multiple stakeholders wanting different things. And so we think about questions like, how can we make decisions with uncertain data while asking for equal opportunity to equally qualified people? How can we find a small set of solutions that are good for infinite objectives, multiple objectives that stakeholders can have? How can we correct data to improve fidelity of downstream models? So as an example, we worked with doctors at Emory and Grady hospitals, so these are ICU clinicians, and we spoke to them about patient data that comes in that has a lot of errors in it. So we asked the clinicians, how can we model sort of these high-dimensional mathematical regions where they expect the true data to lie? So for example, heart rate can only change by so much, or lactate, if lactate is something, then bicarbonate has to be something. So they have these dependencies. So we captured them using mathematical, like polytopes in these mixed integer regions. And then we said, okay, can we correct the data? Can we get the distance from normal physiology? And then can we improve downstream ML? And that actually improved the rate of sepsis prediction quite significantly. We also think about combinations of efficient optimization and learning with trustworthiness. So how can you make decisions over time that are fair to people? So for example, if Amazon is changing prices every time period, how can you constrain those price movements so that the users don't feel cheated? In the optimization and learning segment, we think a lot about the structure of combinatorial decisions, of polytopes. We think about, what if we had to make decisions that look like spanning trees? Can we do that faster by combining continuous optimization perspective and combinatorial optimization? So I love working with graphs, things that are very combinatorial, and so we ask a lot of questions on, how do we find minimizers fast? And then we also have a segment where we are kind of thinking about quantum optimization. So there is a lot of work that we are doing in collaboration with physicists to understand how we can take that traditional knowledge of classical optimization and bring that into that quantum space, so we can have hybrid algorithms that potentially outperform classical algorithms in certain settings. Here is my current research group, and with fantastic students who are very passionate about research. And here is an example of this question of, can we find a small set of solutions that are good for infinite objectives? And we considered medical deserts in the US. So these are regions where people don't have access to a pharmacy close to them, they don't have access to a car. But similar questions can be asked for transplantation centers, how do you position xenografted organs? And so that's our ongoing collaboration with MGH. So in my lab, we work on very theory questions, but we also have strong connections to industry, national labs, and people from other domains like policymakers and lawmakers. So here is the mathematical formulation of that problem that tries to be fair across various objectives. We typically have, we prove theorems about guarantees we can show. So for example, here is a small portfolio with that approximation factor for opening medical facilities across the US with that objective function, which is LP norms of group distances. And recently, we are also expanding that to the space of human AI collaboration. So we are taking that same perspective into saying different stakeholders in a reinforcement learning setting will have different value functions, and an LLM can help us get to those value functions. So for example, in this application, we are working with a collaborator who has a strong connection with an NGO they run a call center, they call expectant mothers. So with limited number of people accessible in the call center, we have to decide which mothers to call. Should we prioritize low income, low education mothers? Should we prioritize people who are not in the system, who are not engaged in the system? Should we try to make a higher engagement? So there could be different reward functions. And then it's the same question, how do I find a small set of solutions or small set of policies that well approximate that entire set of reward functions that human decisions makers can care about. So this work is now actually extending into human AI collaborations. It's using LLM embeddings and understanding like how do we help people navigate that space of solutions that they could potentially get through a system. So we're trying to open that box for them. So I'm very excited to meet all of you later today and tomorrow. There is a list of these projects with some explanations on my website. So that is here. That was the website here. So you can look over that. We also have a very active group culture. We have group meetings. We have weekly meetings. You can talk to some of my current students. And I'm very excited to meet you all and invite you to ORC. And I look forward to talking to you. Thank you.
All right. Next, we have for Doris Likouris.
Hello.
Wait.
Okay. Hi, welcome. Congratulations for getting on with the ORC. It would be wonderful to have you next year. I'm Doris Likouris. I work on sequential decision making, data-driven sequential decision making in human-centric operations. One example that you can think about is content moderation. So if you're Facebook or Twitter, you get something like 1 billion posts every day. Some of the posts need to be removed because they contain content that is inappropriate, illegal. There are different standards based on which you decide what to remove. So how does the pipeline work? When a post comes, you make a classification decision, which means, do I remove the post or do I keep it on the platform? And then these systems tend to have some relatively large volume of reviewers, human reviewers. So Facebook has 15,000 human reviewers, Twitter has 40,000 human reviewers. So what they're doing is that they're using AI initially in order to decide which posts need further attention. So those posts that need further attention are going to be admitted to a queue from which eventually you're going to route to the human reviewers. So really this system, you have this interesting human AI interplay because you're going to make some automated decisions initially, and most of the content needs to be decided automatically. Again, we have 15,000 reviewers and 1 billion posts every day. But also at the same time, for the posts that have higher nuance and maybe more uncertainty, you want to send them to the human reviewers. And the human reviewers have a dual role. On the one hand, they are going to correct mistakes that the AI did. And the second component is that they provide labels for future decisions. So there's this interesting interplay between the data decisions and the humans in this particular scenario. So some applications of interest, generally, I'm working currently with Meta, I have worked with Google, and have been working on collaborating with Stanford Immigration Policy Lab, and also with Airbnb, problems on that space. So these are some applications that you can be thinking. Generally, I'm interested in working with online platforms where you need to make sequential decisions and where you have this interplay between data and decisions, and really some concrete challenges in this particular case. You can think about using limited human feedback in order to train your AI. You can think about strategic interactions. Maybe users have incentives that want to mislead the AI, so you want to think about how to integrate the data. You may think about how to deal with complex behavioral biases that exist in your data. How do you make decisions in light of that? And also I'm interested about thinking about the downstream effect of AI decisions. So this can mean either talking about potential unfairness that may arise or potential long-term effects that you need to take into consideration. And I'm happy to discuss further concrete examples. Some of them arise in content moderation, some of them arise in other applications. Now, with respect to research philosophy, the way that I like to work on is I like to start from a real-world application, and so there's a clear motivation of something that's lacking in the real-world application. And then I like to try to think about what is a formal model that captures formally the particular inefficiency that we are identifying. Why do existing methodologies fail? So in a provable way, can we show that the status quo approaches do not address the challenge that we want to understand? And then can we design algorithms that have provable guarantees, so can provably show that the algorithms perform better, but at the same time they give a rise to interesting insights that can be applied in practice, so practical insights. So that's kind of my high-level research philosophy. I'm generally, content moderation is one thing that I'm currently working on a lot, but I'm generally open to other interesting applications that have these features. With respect to methodologies, I'm generally flexible and I tend to try to learn whatever methodology is better suited for the particular application. Some things that I have been working on have to do about multi-bandits, reinforcement learning, queuing theory, online algorithms, and game theory. These are some tools that I'm generally using, but again, like I'm open to learning whatever is needed in order to tackle the application at hand. So this kind of an overview. I'm not discussing something much more than that. If any of you is interested in discussing more with me, if you are on my schedule, I'm looking forward to talk to you. If you're not, just send me an email and I'm happy to discuss with any of you. I'm pretty flexible tomorrow also. So yeah, so again, welcome, and I hope that all of you are going to be here next year, and I'm looking forward to interacting with all of you in the future. Thanks.
Thank you. All right, because Negin is in class and she's getting a little bit late, what we are going to do is have Ali Awad speak next. This is the clicker.
Perfect. Hello, everyone. All right, just get comfortable.
You can tell he's also coming from class.
Yes, hello, everyone. So I'm wearing a suit because I was in class. That's not my normal way of dressing. So my name is Ali Awad. I'm a faculty in the Operations Management Group at Sloan. I'll tell you a little bit about myself. So before being at Sloan, I was faculty at London Business School in the UK for about 6 years. And before that, I was leading a team of applied scientists at Uber Technologies. And before that, I was in your shoes doing a PhD at the Operations Research Center at MIT. So by and large, what my research is about, what kind of spend my time thinking about is mechanisms, algorithms to match demand and supply, and thinking about various applications of the demand and supply matching. And as you can imagine, these are questions that are very important both in operational contexts, but also in many economic contexts and in many social good applications that I'll kind of list here. And so I roughly divide my work into two areas. One, which is more theory-driven and methodological, where I focus on the design of the algorithms and the decision processes and the mechanisms to match demand and supply. And one that is more, I would say, empirical, applied, and that focuses on new applications, new emerging applications of these ideas to the public sector. And so, what are the challenges when we think about demand-supply matching? If you think like the ride-hailing platform like Uber, or if you think about kind of retail or operations and supply chain. So one fundamental challenge is thinking about preferences. So the demand side is like very complex preferences. Think about how you make decisions to make purchases. Think about a streaming platform that tries to understand how to recommend different movies to you. So I'm showing you here some data that we've kind of plotted representing the network of foods in one application that I've examined. So how do we model these preferences as a network is an important question. And there's another dimension, I would say, is orthogonal, which is the fact that we have oftentimes limited resources on the supply side that we want to allocate to the demand side. And so there is a dynamic element that we don't know necessarily how the situation will evolve, and thinking about the network structure, dynamic network that emerges from this. So when you try to model these challenges, what essentially you're trying to represent is kind of a random network, a certain form of a random network. And so on the theory side, my work focuses on how to model these processes, these behaviors, and how do we design algorithms for the matching of demand and supply that are efficient, equitable, and touches also to market design and networks. And I would say that a lot of what I like doing is combining the algorithm side with the stochastic modeling side. So the contribution is trying to bring two lines of work together. And I've been working in a vast array of applications of this: digital marketplaces, supply chains, ride-hailing, and more recently also on AI alignment. So as you can imagine, these problems are very, very prevalent in nowadays economy. And I'd like to spend more time now on the second line of research, which is focused on public sector operations, which try to bring together both model-based thinking, as in the previous slide, previous stream of work, and also evidence-based research. So thinking about using empirics, rigorous empirics, to understand how do we improve public sector processes. So I've worked across different application areas: culture and education, food security, and more recently on water security. So as you probably know, in the world, there's 1 in 10 person that goes to sleep hungry. So especially in the global south and low and middle income countries, as you probably know, water is one of the big challenges that we will be facing. Like, it's a scarce resource, but also the patterns of water availability are changing and becoming more extreme. And so I have been doing work in the past 5 years on these different aspects, and I'm particularly interested in connecting with students who might be interested in these applications, both from a theory perspective and from an applied perspective as well. And what I meant about going in the field and understanding, behaviors, because as you can imagine, public sector, we don't have as much data as in the private sector. So in many cases, we don't understand the most fundamental, basic kind of behaviors of people. So like one methodology that I've been using in recent years is randomized control trials. And so I'll just end by saying, okay, I've been working with PhD students here at MIT and previously, some of which have already graduated, became faculty. My style of work is quite, I would say, close. I work very closely with the students. I don't work with many students, but I work closely with them. I think the kind of questions that I'm particularly excited about are related to food security, water security this year. And so if you're interested, please let me know. I'll be meeting many of you, and if not, you can approach me. I'll leave you with this note about kind of combination of theory and practice and why both of them kind of matter or are interesting. I started mostly as a theoretician, and in the past 5 years, really got exhilarated by how we can use kind of modeling and data to solve kind of empirical problems. But also, I think there's another feedback loop that by working on real-world problems, you also get new ideas for theory that can be inspiring. So I'll leave you on this note. And sorry, am I very deep?
No, you're very well. Keep talking.
Okay.
No,
Good. So I'll keep talking. Yeah. So that's what I had to say, and I think Nagin is here. Thank you all.
Thank you. So next we have Nagin Golrizai. As I said, everybody's teaching today.
Yeah.
And so we have to. And as you know, you can't get out of class exactly when you want to get out.
Exactly, there are a lot of questions after that. So, first of all, welcome to MIT. And congratulations. We are really proud of having you guys here, and I hope that you guys are also proud of yourself. So, where are my slides? Yeah. Okay, good. So, my name is Nagin Golrizai. You can also call me Nikki. I'm an associate professor in the operation management group. So at a very high level, what I do is that I design algorithms and mechanisms that try to shape real-world problems and decisions. I've been working on online ad markets, collaborating with Google, Meta, to kind of understand this market, try to see how we can optimize that, how to improve, decisions they have. To online retail market, thinking about a lot of problems that Amazon, for example, is facing, or other e-commerce platforms. Or these days I'm working on also carbon markets. There are a lot of interesting algorithmic problems there, understanding how the market performs, how we can improve the auction that are used there. And overall my research is at the intersection of the machine learning, market design is a key component, and a lot of real-time and online decision making that I'm doing in my research. So what drives my research is just these complex markets that we face in various settings, real-time decision making, and other important factors would be strategic agents. So when you're dealing with the market, it's not the data that you are collecting is actually based on the strategic manipulation and strategic actions by the player itself. Whether you are doing pricing, let's say if you do the pricing, the data that you are collecting is influenced by the other sellers that are competing with you, that it could be really strategic. So you want to make sure that you just take the data that you're collecting with a big grain of salt and you don't get tricked by that. So, as I said, the key aspect would be this strategic behavior. These days I'm also working on fairness on digital platforms because a lot of platforms, when they are trying to optimize their decision, they could be short-sighted. Maybe they would say, I want to maximize my short-term revenue, but is that the right decision to make? What if this short-term optimization leads to us losing a lot of market share in the future? And that's where the fairness is coming from. And now I'm investigating that whether if you don't have even regulation in the marketplaces as a platform, do I want to enforce some fairness constraint in order to benefit myself? And when I'm studying this type of question, I'm using data-driven optimization problem, dynamic learning algorithms, and incentive-aware design when you are like very aware of the fact that the data that are collected can be also manipulated by strategic actions. So I've been, as I said, collaborating with various companies across different sectors: Google, Meta, IBM, Liberty Mutual Insurance. I have like this project with Boston Scientific these days. Also getting grant from the government agencies. So then through my collaboration, I try like to make sure I have like practical impact as well as academic impact. So a lot of my research is rooted in theoretical, but it's motivated by practical settings. So now, in terms of what are the things that you can work on if we like end up working together, the newer things that I kind of am working on, it would be this market, the carbon market, that I'm trying like to see how the design of this market can be revisited in order to actually, for us to truly reduce emissions. I have 2 PhD students that are already working on this, but there are a lot of interesting questions in that domain. I'm working on like, when it comes to data-driven decision making, I'm thinking about how can I learn from the data in real-time fashion while being robust to their manipulation and biases. I already have work in that domain, but I'm going to build up on this and continue working on this. The other thing would be this fairness aspect. How can I be fair and profitable at the same time, not only in the short run, but as well as long run? And the last one is very new. I'm actually writing a proposal on that. This is about like a large language model and how large language models is actually impacting the content provider. Now, like with this large language model and the copyright laws that we have, which is quite limited, we are not exactly protecting the content provider. Is there a way for us to design a market so that we can like protect this content provider, so that we can have a healthy ecosystem moving forward? Okay, so then the final thing I want to talk about is about my mentorship philosophy. I really value curiosity, rigor, as well as initiative. So the students that take the initiative in their project, take the ownership, are the ones that are most successful. I closely work with my students. I meet with them like on a weekly basis. If they want to meet more than that, I always like accommodate their request. Try like to co-author papers together. I connect them to industry, help them shape their careers, build their network, and present in top menus. My past students have won several awards. They find jobs in top labs and also publish in top journals. And I look forward to also recruiting new students for the next year. Thank you so much.
And last but not least, it's Vivek Farayas.
Thanks, Georgia. Hi, everyone. I'm that guy. Yeah, let's see. Okay, so I have 2 slides, and you know what I thought I'd do is actually let me introduce myself first. So Vivek Farayas, I've been here since 2007, and I work on lots of different problems. But broadly speaking, you know, over time, it's been about doing things at the interface of optimization and stochastics, like a lot of people here. What I've kind of done a lot of is reinforcement learning. I've done a good amount of that. Applied both the theory of it and also applications of it in a bunch of different areas. You know, outside of all of this, I'll tell you more about my group and what my group has worked on, you know, over time and so forth. But maybe I'll just start with giving you a flavor of some of the things, some of the problems we worked on in actually the last year that I've been pretty excited about. Good. So one problem, right, and this relates, if you don't mind looking at this. One problem, and this relates to policy evaluation in reinforcement learning. So what is reinforcement learning? A lot of you probably know what this is, but roughly it's about learning to control a dynamical system. And one challenge that comes up in controlling dynamical systems is simply taking a policy and evaluating that policy. Okay, like running that policy, simulating that policy. And oftentimes this is hard in systems where you have to simulate these policies over very long horizons. So for instance, let's say you're Amazon, and you want to simulate, and you want to run your entire supply chain with some massive reinforcement learning policy, right? Well, if you ask yourself, what's the time horizon there?
Well, every event is like somebody placing an order, right? And so there's billions of these events. And so you think about a single run, like a single sample pack, right, of a policy, that's like a billion odd things. And so just simply simulating a single policy can take days, literally, right? And you think about like updating that policy, well, that's going to take forever. You'll never be able to do it. And so this was a real problem that we saw that people were facing. And so we worked really hard on trying to understand, is there some structure here where we can make this evaluation task faster? And what we did is we sort of came up with a new idea, something we call the Picard iteration, okay, that basically takes this task and makes it way, way faster. So we've been able to sort of show speed-ups of 1000x, right, on sort of commercial GPUs on this policy evaluation task. And this has been a really lovely combination of doing some very pretty theory and pretty math, but also hacking. And that's sort of common to what I like doing and to people that I tend to work with. Okay? And the interesting thing about this first thing, this policy evaluation task, is led to bigger questions around, as we think about just simply inference in a large language model or in any generative model. Can we take that fundamental task and make that fundamental task faster, right? And that's an even harder question. So we start with like a relatively simple question and make the question harder, more exciting. Another sort of area that we've been very excited about, I'll just pick one or two more here. The second thing over here, right? So I'm personally excited about this. Like one thing I've kind of worked on over time is understanding how people choose, right? So looking at real world data of how people make decisions and then building models of how they make decisions, right? And that's very valuable. One of the things we've observed in the last couple of years is that large language models are extraordinarily good at impersonating human beings. Okay, so the concept is, I tell the large language model, I'm sorry, I don't know your name, but like pretend to be Arya over here, right? And I give it a whole bunch of information about Arya. I say, okay, this is Arya. Now you got to go pick toothpaste, right? Go Arya, go buy toothpaste, right? And so now as opposed to Arya buying toothpaste, it's the language model buying toothpaste, right? And you can ask all these questions about like, okay, what is Arya's elasticity, price elasticity, right? Like as given by this large language model. And this results in lots of fascinating questions around how do you calibrate these things so that they behave like this general population in the room, or whatever general population you want. And you can think like this is very, very powerful, right? You can imagine a big society in a box almost, and you can do all kinds of things with it. So that's been really fun to work on and do. And so last thing I'll say that I've become kind of pretty interested in, because there's sort of really deep things happening on the optimization front over here, is kind of understanding this problem of continual learning. So continual learning is the task of basically you take a massive model and you keep feeding it data. You just keep feeding it data over time, right? So it turns out when you do this, these models, they initially get really good, but then you see this phenomenon of what's called neuron death. Okay, so the model starts like losing capacity effectively over time. There's an amazing paper in Nature on this last summer. We were tracking the same problem and working on it. We've been making a lot of progress on this. So this is a more technical problem, more theoretical problem. It relates to optimization landscapes and things like that. Very exciting. So this is just samples of a couple of things we worked on in the last year. I thought it's the best way of kind of talking about what I do. Just in terms of kind of just overall kind of stats, we tend to publish in, on the one hand, premier ML conferences. If you're familiar with a conference like NeurIPS, we've published, we've had oral presentations at NeurIPS in the last couple of years. This is like, they picked 50 papers out of 10,000 submissions for this. The research group typically, about 2/3 typically goes into academia, a third goes into tech. I take 1 or 2 new students every year. At a high level, we care about doing sort of fundamental research, but fundamental research that has impact. Right, and over time, we've been able to kind of implement this research at a whole bunch of places. And we've also been able to kind of do some of this research to build companies from the ground up. And so, yeah, that's what I want to talk about. Welcome to MIT. Nice seeing you guys. Thanks.